So the analysis of the projective sets only gives you an analysis of definability over the real numbers that reaches, I don't know, it sort of peters out at some point. And there are a lot of open questions that depend on extending this analysis to all of L of R. No. I think if I click on this, it'll work. But I cannot keep going like this. OK, the ultra power axiom works in the fine structure models. But the way I'm going to approach this question is actually by looking at an analogous situation where, for some reason, it's easier to answer the question. OK. Yeah. So the analogous situation is the inner model L of v lambda plus 1 under Wooden's axiom I0, which this analogy between determinacy in L of R and the axiom I0 is well known but not well understood. So it's falling asleep. So I'm just going to sit down and click on the computer every few minutes. OK, so mainly so far, L of R is an extremely well understood model. By set theoretic standards, we've been able to answer many questions about the inner model L of R. An unexpected amount of questions are not independent on the basis of large cardinal axioms. So since L of R is so well understood and L of v lambda plus 1 is kind of mysterious and also not completely invariant under forcing, mainly to this point, L of v lambda plus 1 has been understood by analogy with L of R. So many properties of L of R, for example, the perfect set property can be generalized to L of v lambda plus 1, but with completely different proofs. So what I'm going to talk about is the predictions that the analogy between L of v lambda plus 1 and L of R make about L of R. So there are certain things that are easier to do in L of v lambda plus 1 than in L of R. And so there are certain conjectures that are suggested by the theory of L of v lambda plus 1. And I'm going to try to talk about some of the predictions that this analogy makes that can actually be verified, meaning that the theorems that were proved about L of v lambda plus 1 can be pushed to L of R. Now, one prediction that the theory makes is that L of R should satisfy the ultra power axiom, or something close to it. In fact, some consequences of the ultra power axiom can be shown to hold in L of R. So I'll talk about those. But first, I want to talk about some background. So I wanted to pander in the first slide to the topic of this meeting by pretending to talk about cardinal invariance of the continuum for a second. So this is just the standard notion of an interpretation from model theory. So you can read it if you want. So delta 1 omega is the minimum ordinal that's not interpretable in the second order theory of the natural numbers, so the theory of R with n plus and times. Or in other words, delta 1 omega is the supremum of the lengths of projective pre-well orders of the reals. Saying exactly the same. So delta 1 omega is sort of cardinal invariant of the continuum, except that it may not be a cardinal. And it's obvious that it's between omega 1 and the continuum, but in fact, much more can be said about delta 1 omega, basically because it has to do with definable sets and not arbitrary sets. So the way you can answer questions about L of R is to assume the axiom of determinacy in L of R follows from large cardinals, so true. So Jackson proved this sort of amazing theorem, which just computes delta 1 omega exactly. So in L of R, delta 1 omega is the epsilon 0 infinite cardinal, where epsilon 0 really is the least ordinal, the famous epsilon 0 from Gensen. Okay, so in actuality, delta 1 omega is the aleph epsilon 0 of L of R. And you can actually say a bit more about this, because talking in the real world where the axiom of choice is true, aleph epsilon 0 of L of R must be less than or equal to aleph omega. So there's a lot you can say about delta 1 omega, maybe a little unexpectedly. And cardinals like aleph epsilon 0 never come up in set theory with the axiom of choice. You never see this kind of structure of the continuum. You can think of the question of what delta 1 omega is as an analog of the continuum problem in a definable context. And here there's an answer. It's like Cantor's fantasy of what could happen with the continuum hypothesis. Okay, but I'm not really going to talk about that at all. So what I'm talking about is motivated by the kinds of techniques that are needed to prove Jackson's theorem, which are notoriously difficult. So what comes up in the analysis is, well, you have to analyze all the cardinals below delta 1 omega in this inductive way. And to do that, you classify the ultrafilters on ordinals below delta 1 omega. And then there's this trick that Kettenin discovered to turn a classification of ultrafilters into a classification of all sets of ordinals. And so that's the reason, or one of the reasons, that ultrafilters on ordinals in L of R are so fundamental to the structure of L of R. But I'm going to be talking about ultrafilters in L of R. Okay. So the structure there is very complex. One nice thing that's true is that every ultrafilter in L of R is countably complete. It's just another way of saying that there are no non-principal ultrafilters on omega in L of R, because those wouldn't have the property of there. So Solovay proved that aleph 1 is a measurable cardinal in L of R. So this theorem, every ultrafilter is countably complete, isn't vacuous. There are ultrafilters in L of R. So Solovay showed actually that it's the club filter that witnesses the measurability of aleph. And that's the unique normal measure, aleph 1. He also showed that aleph 2 is measurable. And the only normal measures on aleph 2 are the omega club filter and the omega 1 club filter. So an omega club is a set that's closed under increasing supremums of countable cofinality, not necessarily of uncountable cofinality. Or you can think of it as the club filter restricted to the set of omega ordinals below aleph. But unexpectedly, Martin showed that it's not true that aleph 3 is measurable. Usually in set theory, if you have a pattern that goes for 2 steps, it goes all the way. But that's not the case in this context. So all of the aleph n's for n greater than or equal to 3 are singular with cofinality omega 2. And for years, I think people tried to prove that they were all measurable, but actually they're not even regular. So in the context of the axiom of choice, successor cardinals don't have regular. And then Kettenin and Martin showed that aleph omega plus 1 and aleph omega plus 2 are measurable. And then there are lots of singular cardinals. Jackson showed that, and this involves his analysis, that aleph omega times 2 plus 1 is measurable. So that's I think that everything in between aleph omega plus 2 and aleph omega times 2 is singular. And then sort of bizarrely, aleph omega times 3 plus 1 is singular. So the patterns here are very complex, especially by the standards, I don't know, what you'd expect from what is provable about regular cardinals in ZFC. Basically nothing. So it's quite hard to make conjectures about what should happen in L of R. So many of the conjectures have been incorrect. So sort of need, I don't know, ways to make predictions about what's true, so you can try to prove them. So two ultrafilters are equivalent if, well, basically if they're isomorphic. You can find a set in one and a set in the other that are in bijection, and the bijection moves one ultrafilter to the other. So you can prove this classification of ultrafilters, the very simplest case is the classification of ultrafilters on Aleph-1. And the theorem is that in L of R, every ultrafilter on Aleph-1 is just an iterated product of the unique normal measure, which is the club filter. So an iterated product, well, hopefully you know what the tensor product of two ultrafilters is. Those are the only ultrafilters whatsoever that exist on Aleph-1. So the theorem before said that the only normal measure is the club filter, but now this characterizes all of the ultrafilters. I saw this is in a paper by Jackson, but I'm not sure if it's due to Jackson. It could be Koonin, looks like Koonin. It is very reminiscent of the theorem of Koonin, which is that in L of U, the only ultrafilters on the unique measurable cardinal are the iterated products of the normal measure. Actually, you can prove the first theorem using the second, but this is just the first of many analogies between the structure of ultrafilters in L of R and the structure of ultrafilters in canonical intermodel. So I'm going to talk about ultrapowers a lot, so I need some terminology which is very obvious. So fix an countably complete ultrafilter. Okay, mu is the ultrapower of the universe by U. Ju is the associated ultrapower embedding. And well, mu is well-founded because U is countably complete, so we take it to be transitive. And then the reason I'm saying these sort of obvious things are I wanted to define the notion of an ultrapower embedding in general, which is just if you have two transitive models of ZFC, an elementary embedding from one to the other is an ultrapower embedding if it looks like an ultrapower embedding to the domain model. So there's a countably complete ultrafilter in P, such that Q is the ultrapower by that ultrafilter. Embedding is the associated embedding. Boban, you look. Yeah, so it's just an ultrapower within P. The ultrapower axiom just says that you have two ultrapower embeddings of a universe of sets. You can find further ultrapower embeddings that amalgamate. So the picture, which is, yeah, ultrapower embedding. Okay, so this is the definition of an ultrapower embedding. So it's an ultrapower embedding is just an internal ultrapower of P. So the ultrapower axiom says that these have the amalgamation property, I guess, from model theory. So that just means that if you have these two ultrapowers of V, you can find further ultrapowers that amalgamate the two models and make the diagram commute. So why formulate UA? I mean, it's sort of natural category theoretic principle, but the reason for it is that it's an instance of the comparison lemma in intermodal theory that you can state without reference to fine structure. So because it's sort of, the comparison lemma is central to everything that's done in intermodal theory, and it's sort of all of intermodal theory is centered around proving the comparison lemma. So the definitions of the models are just, I don't know, they're constructed so that the comparison lemma will hold. So if you build any intermodel by the current methodology, UA will hold in it. So for example, if there is a canonical model with a supercompact, then UA should hold in that model. And the point of formulating UA was to try to figure out if there can be intermodels with larger cardinals than the ones that we know. So the current intermodels only go up to a wooden limit of wooden cardinals, or a little bit around there, or maybe to a super strong under some technical hypotheses. But yeah, it's not known whether there's an intermodel with a supercompact, and if you could have refuted UA from a supercompact cardinal, then, well, that would have been an anti-intermodel theorem, but that hasn't happened so far. So if you have a supercompact, you have lots and lots of ultrafilters and lots of ultrapowers. So if you have UA and a supercompact, you get a lot of strength. So you can prove things like the generalized continuum hypothesis above the first supercompact. So in that context, it becomes quite interesting to have UA and supercompacts. And you can look at UA with arbitrarily large cardinals, and so far it seems to be consistent with huge cardinals and 2 huge cardinals. So it suggests that the intermodel theory that we know in some form generalizes to these cardinals. But also UA is equivalent to lots of combinatorial principles about ultrafilters, and it seems to yield a very nice theory of countably complete ultrafilters, so in the context of AC. So it's useful if you want to understand ultrafilters, and it's true in all the intermodels. Okay. The Rudin-Frolic order sort of is the order on ultrafilters if you're trying to decompose ultrafilters into iterated ultrapowers. So one ultrafilter lies below another in the Rudin-Frolic order if you can find an ultrapower embedding from mu to mw that makes the factoring diagram commute. So UA holds if and only if the Rudin-Frolic order is directed. That's just what the definition of UA is saying. Non-principal ultrafilter is irreducible, just if it's minimal in the Rudin-Frolic order, so there's nothing below it, except for principal ultrafilters. And UA allows you to decompose any ultrafilter into irreducible ultrafilters. So you can take the ultrapower and find a finite sequence of irreducible ultrafilters, well, irreducible ultrapowers that compose together to give you the ultrafilter you started with. And more generally, the stronger fact is that if you look at an ultrapower, there can only be finitely many other ultrapowers below it that internally embed back into it. You need the first theorem. So I want to give some examples of irreducible ultrafilters because they're so fundamental to the theory of UA. Yeah? Incompatible. Oh yeah, the Rudin-Frolic order isn't linear. It's UA says it's directed, but if you look at look at the first 2 measurable cardinals, normal ultrafilter on one, normal ultrafilter on the other. You can't embed either of those ultrapowers into the other. You can, even in ZFC, prove that there's an ultrafilter above those 2 in the Rudin-Frolic order. Really big, because it's finite, but there are lots of ultrafilters, at least if you assume large cardinals. Okay, so some irreducible ultrafilters. So normal ultrafilters are irreducible. Even generalized normal ultrafilters, which is what this definition is talking about. So supercompactness measures are all irreducible. There's a sort of general property of ultrafilters that characterizes the irreducible ultrafilters in the inner models, which is called Dodd soundness. It just says that the maximum possible fragment of the ultrapower embedding of the ultrafilter belongs to the ultrapower. So it's the generalization of supercompactness, or it's a version of the initial segment condition. And all Dodd-sound ultrafilters are irreducible. And moreover, under UA, you can prove that the normal ultrafilters and the Dodd-sound ultrafilters are all linearly ordered by the Mitchell order. So there's sort of a classification of them. They're ordered by their rank in the Mitchell order. And in the inner models, they're the kind of ultrafilters that appear on an extender sequence. So under UA, you can say a lot about just irreducible ultrafilters. So you can actually prove that they have a lot of structure. So for example, the ultrapower of an irreducible ultrafilter is always closed under lambda sequences, where lambda is the least cardinal of the least cardinality of a set in the ultrafilter, so the uniformity of the ultrafilter, the size. Except if lambda is inaccessible, when there's some weird stuff that goes on and a bunch of open questions. But if lambda is, for example, a successor cardinal, then actually you get this sort of optimal theorem about the structure of irreducible ultrafilters. And this allows you to analyze strongly compact cardinals and supercompact cardinals. The relationship in ZFC is obviously a huge open question, but under UA it's transparent. Strongly compact cardinals are just the supercompact cardinals or the measurable limits of super. So, and this is sort of optimal because the least measurable limit of supercompact cardinals isn't supercompact, but it is strongly compact by a theorem of. Yeah. So all the theorems I'm going to state are ZFC theorems, but they're going to be about L of R. So yeah, but yes, this analysis depends a lot on the axiom of code. You can't do something like this. And the thing is, the theory of ultrapowers itself breaks down in the context of ZF because Wash's theorem is false. I mean, in L of R, badly failed. But OK, I want to talk about how you can try to transfer some of this theory into models that don't satisfy the axiom of choice. So one way to do it is to combinatorialize all the stuff about ultrapower that I've said. So this is one way. The Lipschitz order is just a generalization of the Lipschitz order on sets of reals to arbitrary sets of ordinals. So a Lipschitz function is one that, if you want to figure out, so it's a function from the power set of delta to the power set of delta. If you want to figure out what f of x is up to an ordinal alpha, you only need to know x up to alpha. So that's what this is saying. So it's a generalization, or it's a version of being Lipschitz of order 1 for functions of metric spaces. OK, and you can say one set is Lipschitz reducible to another if it's the preimage of the other set under a Lipschitz function. So it's just the normal kind of reducibility, but generalized to sets of ordinals. So this is some kind of generalized descriptive set theory. And I think someone else defined it before I. OK, so in L of R, it's well known that the Lipschitz order is linear or almost linear on sets of reals. And it's just a preorder, so this is sort of semi-linearly preordered. It's very close to being a linear order. So if you take any two sets, either one is reducible to the other, or the other is reducible to the complement to the first. So this gives you this kind of familiar diagram from descriptive set theory of point classes and their dual point classes. But it's just a general theorem about arbitrary point classes or point sets. And in fact, the Lipschitz order is well-founded as well on subsets of the power of omega. That, again, coming down to the fact that every set of reals has the property of Baire in L of R. So I'm going to talk about Lipschitz reducibility in the context of UA. Ultrafilters are subsets of the power of some set. So if you have an ordinal delta, you can look at the subsets of the power of delta and look at Lipschitz reducibility on those things. So theorem is that any ordinal delta under UA, the Lipschitz order is just a linear order on the ultrafilters on delta. And it's actually a well order. So this is another kind of classification of ultrafilters because they're uniquely determined by their rank in this order. More generally, in ZFC, the right generalization of this order is called the Kettenin order. It was first defined by Kettenin in strongly compact cardinals and other cardinal sins or something like that. He had a lot of interestingly named papers in the 70s. So a Kettenin function is just one that reduces ultrafilters to ultrafilters. So it's a Lipschitz function that reduces ultrafilters to ultrafilters uniformly. And these are much better behaved than arbitrary Lipschitz functions in the context of choice. Lipschitz functions are very complex, but these come down to countable complete. So Kettenin reduction is just reducibility under Kettenin functions. And so you can prove that the Kettenin order is well-founded, whereas with the Lipschitz order, I have no idea. Yeah, so this is just in CFC. So, that's me. Kettenin proved the well-foundedness of the order that he looked at, which was restricted to weakly normal ultrafilters, but it's a different proof for arbitrary ultrafilters. It looks a lot like the proof of the Mitchell order as well. The Kettenin order is kind of a generalization of the Mitchell order. If you look at normal measures under the Kettenin order, it's just the Mitchell order. And okay, if the Kettenin order is a well order for all ordinals delta, then the ultrapower axiom is true. So that sort of explains why this Lipschitz ordering of ultrafilters is so important under UA. The entirety of UA comes down to the linearity of that order. It's sort of an interesting question whether the linearity of the Lipschitz order implies UA, because that would tell you that UA is sort of a determinacy principle. Because linearity of the Lipschitz order on ultrafilters is a consequence of a kind of determinacy of a long game, but that's open. So if you know that the Kettenin order is linear, then every ultrafilter is uniquely determined by its rank in that order. When I say ultrafilter, I mean countably complete. So it follows that every countably complete ultrafilter on an ordinal is ordinal definable. So that's a kind of closeness between the universe and Hod that's and hereditarily ordinal definable sets that's provable from UA. So you get things like if UA holds and there's a supercompact cardinal, then V is a generic extension of Hod. Yeah, okay, so Matteo asked, if you couldn't hear, whether it's known that there's a model of CFC plus large cardinals where UA fails. And the answer is yes, it's really easy to kill UA by forcing. So for example, UA implies that there's a unique normal measure on the least measurable cardinal. But you do Kunin-Paris forcing, you can make there be 2 to the kappa many normal measures on the least measurable cardinal. And that forcing is going to preserve all large cardinals. So there's no way to prove UA from large cardinals. We'll talk about sort of a proof of UA from large cardinals later, though. So by some strange coincidence, it's also possible to definably well order the ultrafilters in L of R. And so you get the analogous theorem. Every ultrafilter on an ordinal is ordinal definable in L of R. So that's sort of a strange coincidence of the structures of canonical inner models of CFC and this model L of R. And the first theorem can sort of explain the second. So the question is this coincidence more than a coincidence? So for example, is the ultrapower axiom true in L of R? But to even make sense of the question, you need to sort of get rid of all the ultrapowers in the ultrapower axiom, because ultrapowers, as I was saying before, really are very ill-behaved in L of R. So they never satisfy Wash's theorem, which is fundamental. So the embedding associated, so the ultrapower embedding associated with an ultrafilter is never, an ultrafilter on an ordinal is never going to be elementary. So you sort of want to get a combinatorial version of the ultrapower axiom. And we've seen 1 or 2 of them. So one version is for all ordinals delta, the Kettenin order is linear on the countably complete ultrafilters on delta. So I said before, that's equivalent to the ultrapower axiom in the context of AC. but it makes sense in L of R to ask this question. That's open, but it's basically what I'll be talking about. And then you can define the root and frolic order combinatorially, and as I said before, UA is equivalent to the directedness of the root and frolic order. So another combinatorial version of UA would say that for all ultrafilters on ordinals, the root and frolic order is directed. So when you restrict it to ultrafilters on ordinals. I don't want to talk about ultrafilters off ordinals because I don't think that there's any UA-like behavior for this. So in the context of ZFC, every ultrafilter is equivalent to an ultrafilter on an ordinal because you can well order the underlying set. But in the context of L of R, that's very far from true. But so these two characterizations of UA are equivalent, even just in ZF plus DC, which is sort of annoying to prove because you can't take any ultra powers. But the same proof works. Yeah? Well, that's true. Yeah. So no, it's useful. We'll see that it's quite useful. So that's part of the reason for these. So yeah, let me repeat what Ralph said. So Ralph asked, you could also formulate this ultra power axiom in L of R by saying that UA holds in Hod sub x for all x. And this is known to be true because Steele gave an analysis of the inner model Hod sub x in terms of fine structure. And that since Hod sub x has a fine structural analysis, it must satisfy the ultra power axiom. There's a comparison theorem. So that's another way you could talk about UA in L of R, and we'll see that's important to the structure of ultrafilters. But this is, if you want to understand the countably complete ultrafilters of L of R, this is the way to say that they satisfy the ultra power axiom. Okay, so I'm switching gears and talking about extremely large cardinals, so way beyond the kind of cardinals you need to prove determinacy in L of R, and an analogy between those large cardinals and determinacy. So it turns out the best evidence that L of R does satisfy UA comes from these large cardinal axioms. So for example, Reinhardt proposed the axiom, there's a non-trivial elementary embedding from the universe of sets to itself. This was in the early days of large cardinals. And Kettenin showed that if you assume ZFC, there is none. So Reinhardt's principle is just false in ZFC. But sort of, if you're a large cardinal theorist, you want to get as close to the edge as you can. So people have looked at the proof, and you can see that the proof actually rules out any elementary embedding from a double successor level of the cumulative hierarchy to itself. So then if you have any elementary embedding, like the one in Kettenin's theorem, but restricted to a rank, it follows that that rank is strictly less than the double successor of this cardinal lambda, which is just the supremum of the iteration of J starting with its critical point. That's because this supremum is fixed by J, if it's even in the domain of J. And so you could restrict J down to an elementary embedding from V lambda plus 2 to V lambda plus 2 if it were defined there, and that would be false by Kettenin's theorem. Okay, so I want to talk about the analogy between determinacy and these kinds of weird elementary embeddings at the level that's as close to the Kettenin inconsistency as possible in ZFC. So it turns out that the descriptive set theory, or the theory of definability over V lambda plus 1, assuming the existence of these embeddings, or lots of them, resembles the structure of V omega plus 1 that holds under determinacy axioms. So there's a sort of correspondence, but it's not understood why there is a correspondence. So for example, I put some corresponding axioms and from determinacy and elementary embeddings, but don't hold me to them. So yeah, it's an analogy, not a theorem, and it's not understood at all. So The delta 1,1 determinacy has something in common with the existence of an embedding from v lambda to v lambda. Pi 1,1 determinacy is something in common with a sigma 1 elementary embedding. Projective determinacy has something in common with sigma n embeddings for all n. And determinacy in L of R somehow has very similar consequences to the existence of an embedding from L of v lambda plus 1 to itself. You have to specify that the critical point is below lambda, because you could have the critical point above lambda. That follows from the existence of a measurable cardinal. So we want to be way beyond that. So the idea is that these embeddings are getting more and more elementary. So at first, they're sigma 1 elementary on the sigma 1 subsets of v lambda plus 1, then all the definable subsets, and then definable over definability. So on L1 of v lambda plus 1 and L2 of v lambda plus 1, and the sort of hierarchy goes up all the way to L of v lambda plus 1 and beyond. So this principle that there's an embedding from L of v lambda plus 1 is called I0. I'm not going to explain the reason it's called I0. And I'm going to talk mostly about the axiom I0 because there's this correspondence between L of v lambda plus 1 and L of R that is sort of fruitful. Okay, so going forward, I'm going to talk about I0. So lambda is going to denote some cardinal such that there's an elementary embedding from L of v lambda plus 1 to itself with critical point below lambda. So just to sort of explain or give some examples of this analogy, an L of v lambda plus 1, Wooden showed that lambda plus is a measurable cardinal. It's measurable via, well, not the club filter, because again, you can look at the omega club filter and the omega 1 club filter and the omega 2 club filter. And so the club filter itself is not a measure because it can extend to distinct filters. For example, if you restrict to ordinals of countable cofinality, club filter basically an ultrafilter by a theorem of Kramer. There's sort of independence results for the higher cofinalities. It's open whether the club filter on the omega club filter on lambda plus is ultrafilter. And Kramer showed that every subset of phi lambda plus 1 has a perfect set property. So these are like fundamental consequences of the axiom of determinacy in L of R. Every subset of phi omega plus 1 has the perfect set theory. Davis, Morton, Davis. No, I can't remember who proved the perfect set property in L of R. Sorry. Yeah, so every subset of v lambda plus 1 either has cardinality lambda or else has an embedding from the perfect, yeah. It's even stronger than that. It's called a lambda splitting perfect set property, so the tree splits a lot. Okay, so and just a couple more examples. Very important cardinal in L of R is it's the analog of delta 1 omega, but for arbitrary sets of reals. Theta, so it's just the supremum of the pre-well orderings on the reals that exist in L of R. So it's the least ordinal that is not of the form, so it's not the range of a function on R that belongs to L of R. And theta of L of v lambda plus 1 is just the analogous cardinal in L of v lambda plus 1. So you just take the R's, replace them by v lambda plus 1s. L of R, I should probably say, is the same as L of v omega plus 1. So the correspondence is between lambda and omega. So Moscovakis showed that theta of L of R is weakly inaccessible in L of R. It has many large cardinal properties. And Wooden showed the same sort of large cardinal properties hold of theta in L of v lambda. So there are a lot of commonalities. They run pretty deep. But I want to say, like, the theory of L of v lambda plus 1 is completely mysterious, down low even. So for example, it's not known whether lambda double plus is measurable. So that would be analogous to omega 2 being measurable. Or it's not even known that lambda double plus is regular. It's not known whether lambda triple plus is singular. So basically, none of these combinatorial questions about ultrafilters locally have been answered. It's not known whether any partition properties hold. So infinite exponent partition properties are a well-known consequence of determinacy, but in LFV lambda plus 1, you can't take this exponent up above omega 1, at least assuming AC in the background theory, because the partition property with exponent omega 1 on any cardinal implies that there's no omega 1 size sequence of reals. So no uncountable well-orderable sequence of reals. So you can't go above omega 1, so that's sort of a difference between the structure in L of R and the structure LFV lambda plus 1. Okay, you can ask about the uniformization property, and that's open. You can ask about coding lemma, that's open. So there's a version of the coding lemma, but not this local kind of coding lemma. So in L of R, every subset of omega 1 is definable, is in L of a real. That can't be true in L of V lambda plus 1, but this is the analog. If I talk for more than a minute, then it just freezes. Okay, so the global theory of L of V lambda plus 1. So I want to talk about ultrafilters going up way above lambda double plus and stuff. So Kettenin showed that every countably complete filter on an ordinal in L of R can be extended to a countably complete ultrafilter. So this is a version of strong compactness for omega 1. So there's sort of this pattern where tiny cardinals in L of R have very large cardinal properties. The proof uses the Martin measure on Turing degrees, which tells you that actually there's another version of strong compactness. There's a countably complete fine ultrafilter on P omega 1 of R, basically the Martin measure. And then you can just use the usual proof that countably complete filters extend to countably complete ultrafilters using the ultrafilter on P omega 1 of R instead of an ultrafilter on P kappa. Yeah, the Martin measure on the Turing degrees is the filter generated by the cones. So the cone of Turing degrees is just the set of degrees above some fixed degree. And you can generate a filter, countably complete filter, using those cones, and consequence of determinacy is that it's an ultrafilter. Sort of surprising. P omega 1 of R, the Turing degrees are the surjective image. You can think of a Turing degree as a countable set of reals. Really, you're looking at the principal ideal below the degree. Okay, there's no analog of this for L of V lambda plus 1, but you can show in L of V lambda plus 1 that every lambda plus complete filter on an ordinal extends to a lambda plus complete ultrafilter. So the exact theorem that Kettenin proved, I proved in L of V lambda plus 1, and it actually uses the Kettenin order. It's proved by induction on the Kettenin order on lambda plus complete filter. So I didn't define the Kettenin order on filters, but just Kettenin reducibility. Okay, more of this analogy. An atom of a filter is a positive set for the filter, such that when you add it to the filter, you generate an ultrafilter. A filter is atomic if every positive set contains an atom. A positive set is like an F non-null set. It's not in the dual ideal of F. So these are the kinds of sets that you can add into F and still generate a filter. Okay, so it's a theorem of Kekris, Kleinberg, Moskvakis, and Wooden that any strong partition cardinal has an atomic club filter. You can actually characterize the atoms of the club filter. They're the stationary sets that don't reflect into themselves. It's open whether this is true for arbitrary regular cardinals in L of R, but you can actually do it in L of V lambda plus 1. So this is the first, not very first, but first instance I've mentioned of a theorem that's known for L of V lambda plus 1, but not for L of R. So sort of stronger theorem about the ultrafilters in L of V lambda plus 1 is that they almost satisfy the ultrapower axiom. So this is sort of an instance of large cardinals implying the ultrapower axiom, strange way. So to say the sense in which they almost imply the ultrapower axiom, let me define some obvious terminology. The alpha level of a well-founded partial order is just all the things of rank alpha in the partial order. And obviously P is linear if all its levels size 1. But in L of V lambda plus 1, all the levels of the Kettenin order have cardinality strictly less than lambda. So it's sort of a boundedness on the width of the Kettenin order. So the Kettenin order is almost linear. So this version, combinatorial version of UA almost holds in L of V lambda plus 1. I mean, because the levels of the Kettenin order are small if you think lambda is small. I mean, huge, but you can't do any better than this because Kettenin reducibility actually isn't linear in L of V lambda plus 1. It's provably not linear. The normal ultrafilter, the omega club measure, basically is not comparable with the omega 1 club measure. And the reason is this background assumption of choice in V. So there's sort of this incompatibility. If you could compare these two ultrafilters and you could prove omega 1 is measurable, sort of strange stuff going on there. So the conjecture is that the analogous theorem should hold in L of R. So I think this sort of justifies making this kind of conjecture, even though it's hard to see how you would verify it. So it's just switching the lambda to an omega. Yeah. No, actually, okay, so Matteo asked whether the ultrafilter is of any cofinality on lambda plus, so that the delta club filter for each regular delta below lambda should be incomparable, which would contradict the theorem, so it can't be true. But once delta below lambda, sorry, say gamma is your regular cardinal below lambda, once it gets to be a measurable cardinal, it's possible to compare the ultrafilters. It's not inconsistent anymore, whereas for omega 1, you would get measures on omega 1. Okay. So I'm conjecturing some form of the ultrapower axiom in L of R, which would be very useful. Okay, so it's more conjectures. The Rudin-Kiesler order, it's just what you know and love. I don't know why I wrote it in a confusing way. One ultrafilter is below another in the Rudin-Kiesler order if you can push it, the second one forward and get the first. Or this thing about so the theorem is that in L of V lambda plus 1, if you look at the countably complete ultrafilters on ordinals, they never have lambda many predecessors. So the Rudin-Kiesler order is sort of, well, this is sort of analogous actually to the thing about the Rudin-Frolic order that was proved under UA. So the Rudin-Kiesler order is locally small. Below any point, there's only a few other points. You think lambda is small. So the Rudin-Kiesler order is an extension of the Rudin-Frolic order. So this is stronger than the generalization of the UA theorem to L of V lambda plus 1. So the Rudin-Frolic order also has this property. So whereas the ultrapower axiom theorem said that the Rudin-Frolic order is locally finite under UA. So this is analogous to a consequence of UA. So conjecture that no ultrafilter on an ordinal has infinitely many Rudin-Kiesler predecessors in L of R. This seems very plausible. Seems plausible that you could just do this using combinatorics, but I couldn't. But actually, you can transfer these. Some of these conjectures actually you can prove, or versions of them. So there have been no instances of that before, so that's sort of why I thought it was interesting, why I'm talking about it. So up until now, there's been no insight about L of R gained from L of V lambda plus 1. Or you can make all these conjectures, but none of them has been proved. But here's some versions of the theorems that actually turned out to be provable in L of R when I tried. So I actually really did prove one theorem about L of V lambda plus 1 and try to prove it in L of R, and it sort of worked. OK, so in L of R, the exact analog of the UA theorem is true. So no ultrafilter on an ordinal has infinitely many root and frolic predecessors. I guess you sort of have to say what the root and frolic order is in L of R, but it's exactly what root and frolic defined, not the thing about ultrapowers, but some combinatorial. So also, you can restrict to nicer ultrafilters when you're trying to prove this conjecture about the root and Kiesler order. So semi-normal ultrafilters are extensions of the club filter. They don't actually have to be normal, it turns out. If you look at large enough cardinals in L of R, there are extensions of the club filter that aren't normal. And actually, Jackson, at least according to Jackson, the structure of semi-normal ultrafilters is central to extending his theory. It says so in his handbook article. And you can show in L of R that no ultrafilter on an ordinal has infinitely many semi-normal root and Kiesler predecessors. And I should say about the first theorem, about the root and frolic order, it lets you do this decomposition of ultrafilters in L of R into irreducibles. So that seems pretty useful. Then you just have to analyze the irreducible ultrafilters and their iterations. OK, the proofs of these theorems use Steele's analysis of Hod of L of R. So that was what Rolf was asking about before. These analogs of UA and L of R are literally proved by using the fact that UA holds in Hod sub x for each x. So you sort of look at an ultrafilter, and you look at its restriction to these models of choice in UA, Hod sub x, and you can apply all the UA theory that's developed under AC and sort of constrain the structure on ultrafilters in the model L of R. Also, the restriction of U to Hod sub x is in Hod sub x because of this theorem that every ultrafilter is ordinal definable. Why you can do this. OK. So the last thing I'm going to talk about is products of ultrafilters, sort of completely combinatorial questions about ultrafilters. But they are relevant to the UA question, I'll say on the next slide. So if you have two ultrafilters, you can try to form a product of them. There are really two ways to try to do this. The Cartesian product is like the measure theory, the product of the measures. Well, it's completion. So it's just a filter generated by rectangles. Sets of the form A times B, where A and B are large with respect to the two ultrafilters. And you can also define these tensor products, which are what I called iterated products before. So it's like you just use the ultrafilter quantifier. So a set is large with respect to the left tensor product, I guess, if the set is a subset of x times y, so it's large if for almost all x with respect to u, for almost all y with respect to w, xy is in the set. And this thing, unlike the Cartesian product, is not symmetric, so you can define this other version of the tensor product, the right tensor product. Same definition, flipping the quantifiers. Okay, u times w is contained in the product of u with w. Just, it's pretty obvious. But usually, all these ultrafilters are different. So the tensor products aren't commutative, and the Cartesian product has the flaw that it doesn't give you an ultrafilter. So there are problems with all the products on ultrafilters. In special cases, though, u times w can be an ultrafilter. So Blas showed, and he talked about these filter products a lot in his thesis. So this is a pretty old result from like 1970, that if w is u complete, meaning just look at the cardinality of U, really the question is about the uniformity of U, then U times W, the Cartesian product, turns out to be an ultrafilter. And in that case, since U times W is contained in the tensor products, they all have to be equal because U times W is a maximal filter. So any extension of it is equal to it if it's a filter. So the question is this the only way that U left product W can be equal to U right product W? So it's sort of trying to prove a converse to Bloss's theorem in some way. You can't prove the exact converse of Bloss's theorem. Well, maybe it's not really a converse of Bloss's theorem at all. Shouldn't have said that. Okay, so the question is, if the ultrafilter quantifiers commute, must the rectangles generate an ultrafilter? Okay, what's the relevance of this to someone who's interested in large cardinals? It's that the ultrafilters extending U times W are the amalgamations of the ultrapowers. So the ultrapower axiom is all about these extensions of U times W. The tensor products are this canonical way of amalgamating the ultrapower. So this is with arbitrary elementary embeddings, not necessarily ultrapower embeddings. So there are two possible amalgamations that you can define. Basically, they're the only two. So these come up everywhere in large cardinals. The quantifiers commute if the ultrapowers commute, sort of strange coincidence. People call this the commuting ultrapowers lemma. The theorem that Bloss proved was that if U is complete past the size of W, then the product is an ultrafilter, so the ultrapowers commute. So that's a theorem of Kettenin that people use, but the connection is sort of not seen because people aren't doing ultrafilter combinatorics. Probably Kettenin knew because he did a lot of ultrafilter combinatorics. Anyway, so UA implies that if U times W is an ultrafilter, well, no, U times W is an ultrafilter if and only if the ultrafilters commute. Sort of actually uses all the UA analysis of irreducible ultrafilters. So all the hardest theorems of UA are used to prove this simple combinatorial result. So it seems like probably that's unnecessary. And it turns out that by very different methods, although sort of motivated by the UA method, you can prove this, assuming the GCH. So this is a sort of different kind of confirmation of a prediction. I'd say that these theorems of UA sort of guide you to, well, what should be theorems of ZFC. Here I had to use GCH. Probably, I don't know if it's going to be independent. Like an interesting question. Okay, so in ZF, the theorem is not true. So U times U is never an ultrafilter. There are pretty obvious distinct ways to extend U times U. There are the tensor products, but there's also the trivial product. The diagonal, basically, you add in the diagonal to U times U. You get basically U. Okay, so but Elliott Glaser pointed out that in L of R, there is an ultrafilter which commutes with itself. So the only way that can happen is if the underlying set of the ultrafilter isn't linearly orderable. And actually, the underlying set of the ultrafilter in question is the reals mod omega to the omega mod finite. And you have the 0, 1 law for, say, Lebesgue measure. So you get an ultrafilter on that structure, just coming from induced by Lebesgue measure. You can think of it as mod finite invariant sets are either measure 0 or measure 1. So that's an ultrafilter on the quotient. And it commutes with itself. That's just Fubini's theorem. So the equivalence is false in L of R, but you can ask about ultrafilters on ordinals, where consequences of UA are, I don't know, the structure is like the UA structure. And so you can prove if you have ultrafilters on ordinals, then you U times W is an ultrafilter if and only if the ultrafilter is. So I'm going to give you the proof just because it's an easy application of a very deep theorem. And then I'm going to end. Yeah, I'm going to wrap up. OK, so the theorem is pretty easy. So take U and W on an ordinal delta and assume that they commute. And we have to show that the product is an ultrafilter. So fix A contained in the product, delta times delta. You have to show that it's measured by U times W. So we have to show that there's a rectangle of the form, I guess, D times E that is either contained in A or contained in the complement. So because you're in L of R, every set is ordinal definable from a real. So fix some real. And let U bar be the restriction of U to Hod sub X. W bar the restriction of W to Hod sub X. They're both in Hod sub X by Kunin's theorem that every ultrafilter is ordinal definable. So in Hod sub X, now U bar and W bar commute. The reason is that they commute in L of R, and that is downwards absolute. And Steele proved that in Hod sub X, GCH holds and UA holds. So you can apply either of the theorems from the last slide to show that U bar times W bar has to be an ultrafilter if U and W commute. So it follows that U bar times W bar measures set A. Either A has, because U bar times W bar measures every set. But from that, it follows that U times W measures A. Because you got a rectangle, it's contained in A or its complement, it's still true, L of R. So a really easy application of Steele's theorem, which is a very hard theorem. So I thought it was sort of nice. Sorry, I said, I think in the beginning that I'm always assuming ADL of R. Or I didn't say it. I meant to say it. I wrote it on the slide. Yeah, you can't prove Steele's theorem without ADL. OK, so all I wanted to say is, what can you take from this? The analogy between L of R and L of V lambda plus 1 goes both ways. There's some evidence that UA holds in L of R. Maybe it's sort of weak evidence. Some version of UA should hold in L of R. And let me conjecture all the things that were proved in L of V lambda plus 1 should actually hold in L of R. Okay. Thank you. If you have any. Mm-hmm. I think it. OK, I'll repeat the question. Yeah, the question was whether the space of ultrafilters on an ordinal or on a set is of any interest in L of R. And the answer is yes. To me, it's of interest. Because, I mean, the Kunin theorem that every filter extends to an ultrafilter in L of R tells you that it's the countably complete ultrafilter space is actually Lindelof, I think. So it has the kind of nice structure that the space of ultrafilters on a set, its Stone-Check compactification of a discrete space has. So yeah, I think it is interesting, probably, maybe. But for me, I've never been able to do anything with topology on ultrafilters. My problem, probably. But I've never been able to prove a theorem using topology. I mean, L of V lambda plus 1. Yeah, there's some connection, I think. I didn't use their results. OK. Yeah, no, if you have a question, ask, and I'll answer very quickly, but I doubt it. OK, let's say no one has a question.